I'm Charles Parker, the VP of Machine Learning Algorithms here at BigML. We'll be talking mostly in this webinar about our new technology that we're rolling out in the fall release. The main point of the fall release, the main new bit is going to be topic modeling. One thing you'll notice about me is I'm not Paul Peterson, who normally gives these webinars, but hopefully I'll live up to Paul's high standards. And as always, you can contact us via info or on Twitter to get more information about the webinar. So topic modeling, the main meat of the fall release for BigML. What is it, first of all? Well, topic modeling, in short, is a method for discovering structure in bits of unstructured text. So usually when you come to us with your data at BigML and you have text data, it's in an unstructured form. Good examples of this are news stories or emails or web pages. Generally, the data, the text data, isn't in a nice row-column format that you usually, of the sort you usually prefer to do machine learning. You have just kind of a random blob of text for each instance. And so discovering structure in that text is going to be very important. Our main algorithm that we use for topic modeling is essentially an optimized version of LDA, Latent Dirichlet Allocation, and it was introduced by David Bly, Andrew Ng, and Michael Jordan in 2003. This was when David Bly and Andrew Ng were grad students, so if you ever wonder what people who are incredibly smart were doing when they're grad students, it turns out they were doing things that were incredibly smart. So yeah, this is some of their very early work by Bly and Ng, and turns out to be great work that has stood the test of time. And of course, the main thing that we bring to the process, bring to the algorithm, besides making it scalable and run as fast as possible, is that it's now BigML easy. So we try to make it as easy as possible for people who aren't used to writing computer code to use the algorithm, and also we try to make it beautiful so that you can see the results of the algorithm in a way that's meaningful. So before we really get into the meat of talking about latent Dirichlet allocation, let's talk about the taxonomy of BigML resources that are available to you now and where topic modeling fits into that taxonomy of resources. As you know, in the first row, we have kind of our basic data exploration tools, things to create data sets from data sources, and also the ability to do correlations and statistical tests. In the second row, we have the traditional supervised learning models, so decision trees, ensembles, logistic regressions, and the ability to evaluate those models. In the bottom row there, skipping a row, you have the tools we recently released for automation, WizML, scripts, libraries, executions. And then in the third row, you have this cluster, for lack of a better term, of techniques that we kind of lump into the category of unsupervised learning. And to kind of emphasize the kind of traditional way of looking at data science machine learning tools, we've updated our interface a bit to be a realization of that taxonomy. So you can see we have sources and data sets here in the new version of the interface, but also we've put all of our supervised techniques under a single menu, the unsupervised techniques under a single menu, and the ability to make predictions of various kinds under a single menu as well. And then over here we have the automation menu, the WizML menu for your scripts, libraries, and executions. So unsupervised learning, as I said in this slide, unsupervised learning is a bit of a catch-all for many possible machine learning techniques. So let's talk a little bit about what we mean generally by unsupervised learning. As with supervised learning, you're going to learn from instances. So each row in your data is entity instance, or have more data essentially, make a prediction, know about its structure and where it fits into your data set. Each row in the data is an instance. And then each column in the data is a feature, so information about that instance, some sort of attribute of the instance. So this, so far, is the same as supervised learning, but unlike in supervised learning, there's no label. So with supervised learning, with decision trees, models, logistic regression, there's something you're trying to predict. There's a label for the instance that you're trying to create a model to infer. There's kind of a variety of things you can do that fall under this sort of rubric of possible techniques. There's a lot of different things you can do. It's different from supervised learning in that you don't have a fixed goal. In supervised learning, you're trying to predict the label. With unsupervised learning, basically you're just trying to discover some sort of structure that gives you insight about the data. So it's a lot more open-ended. In clustering, you're trying to find which instances are alike. So in the little pictogram we have there, 3 rows are blue. We've decided that those 3 rows are alike in some way. With anomaly detection, you're kind of trying to do the opposite. You're trying to find which instances in your data are not like the other instances. So that red row there is sort of an example of a row that's being called out as being in some way dissimilar from the rest of your data. And then association discovery is trying to find sort of one or two or three predicate rules that can predict one feature value from another. So association between features in your data set. And so where does topic modeling fit into this? As we said, topic modeling, it is an unsupervised technique, and it works on the text fields in your data. What it's trying to do is find the hidden topics that model the text. So basically, we're going to imagine that the text fields in your data are generated from topics, and each of those topics is responsible for generating some part of your text data. So the questions here, first of all, how is it that this differs from the traditional text analysis that BigML already offers? Secondly, what does the output of the topic model look like, and how can we use it? And then third, it is unsupervised, but it's still a model. So with supervised models, there's a goal. There's something that these models are designed to do. There's a reason that they exist and are structured the way they do. What is motivating an unsupervised model, an unsupervised topic model, to look the way it does? So let's just talk for a moment about our traditional text analysis. What we get in for our instances are blobs of text like this. And the first thing we do is we do word stemming. So basically, we look for the root of all of the different words in our blob of text, and we map those roots to the same lexeme. So essentially, you have the words great and greatness in this blob of text. We decide that because those words have the same root, great, they're essentially the same. They have very similar semantics. And then the next thing we do is remove stop words. So words like be, not, of, are, traditionally don't give too much information or too much insight into exactly what the text is about. And so we remove those words unless you specifically ask for their inclusion. And then we also remove some words that we find either don't occur enough in the collection or occur too much in the collection to be useful, basically preferring words that occur in several instances, but not all of them, words that are probably going to be discriminative between instances. And then after that, after we've kind of pre-processed the text, we can turn it into a bag of words where we count each word into a vector. So essentially here we have the word great appearing 4 times after we've done the word stemming, and we have the words afraid, born, and achieve having occurred 1 time. And you can see that basically this is just going to give us a bunch of numeric features that we can use for modeling. So great is assigned the value 4, afraid is assigned the value 1, born, achieve are both 1, just because those are the counts of the words in the processed text. And then when we go to model, when we go to learn a decision tree on these words, we can basically just use those counts as numeric features. So we can do a split like the token great occurs more than 3 times, the token afraid occurs less than 1 time, and eventually you can work your way down in the traditional decision tree fashion to a prediction using those numeric features. So let's just see what that looks like using a text data set here. And so the data set I'm going to be working with for most of this demo is the StumbleUpon data set. And this was a Kaggle data set from a while ago. And basically, the goal in the StumbleUpon data set is to predict whether or not a bit of web content is evergreen. What do we mean by evergreen? So some pieces of web content, like news stories, for example, or memes, have a shelf life. They won't be as relevant in 5 years as they are today. And so people are a lot likely to reread those things or to recommend others to reread those things in the future. On the other hand, there are some pieces of web content that we'll call evergreen, which retain their semantic value and usefulness as time moves forward. So the classic example of this is a recipe. A recipe for cookies is probably going to be just as relevant today as it is tomorrow and in 5 years, food trends notwithstanding. So we have a data set of these things. Some of them are labeled 1, which is evergreen, and some of them are labeled 0, which is ephemeral or non-evergreen. These are the transient sorts of content that I was talking about before. And the 2 features we have in this data set that we're going to use are the boilerplate, which is basically just the text title and various attributes of the web page, and the URL of the web page. So the URL of the web page and its content, essentially, are the features we have here. In the traditional version of the StumbleUpon dataset, there's a whole bunch of numeric features included. We're not going to use those here. We're just going to use the raw text. And so let's see what happens if I do a one-click model here to predict the label. Usually, these models with only 2 features are going to proceed very quickly. A model with only 2 features only has to look at 2 different things, and that doesn't take very much time. However, here we're generating a feature for every possible word in the text, all of the different words that we're counting. So we're going to have, it's going to take a little more time than just your average 2-feature model. And here's what we get. So the first thing it looks at is the boilerplate, the content of the web page. And the first thing it's going to ask is, does it contain the word baking? Obviously, that's a very discriminative feature. As I said before, right, if it's a recipe for cookies, probably it's going to be evergreen. And in fact, if it's a recipe for banana bread or brownies, it's also probably going to be evergreen. So if it contains the word baking, that's a pretty good sign that you're looking at something that's non-ephemeral. So that's pretty good, right? As far as it goes, single words, counts of single words are pretty informative in this domain when you're trying to determine whether or not a web page is evergreen. And importantly, you'll see that if we go down here, this is the path of the non-evergreen instances. All it's looking for in the first 5 or 6 splits here is words that relate to cooking, right? So it doesn't contain baking, doesn't contain recipes, doesn't contain cooking, doesn't contain food, doesn't contain flavor, so on and so forth. So this is essentially what we've learned about this data, is that you can predict whether or not content is evergreen, basically by trying to figure out whether or not it's about food. That's a little bit of a reductive view of this data set, but it's useful for prediction. So that's what our traditional text analysis looks like. So let's kind of compare the two before we really get into topic modeling. First of all, text, as we said, it creates thousands of hidden token counts. So basically, it kind of extrapolates your text into a series of numeric features, into a series of token counts. Topic models create a few dozen topics that try to model the text. So it's not going to create, possibly thousands of features. It's only going to create a few dozen. Token counts are independently uninteresting. So basically, if you say this blob of text contains baking, it doesn't really tell you that much about the text. Because baking, it's often associated with cooking, but it's used in a lot of English idioms like baked into the cake, for example. So if you see the word baked, it's not a sure sign. All you know is that it contains the word and there's some probabilities associated with it. Topics, on the other hand, we're going to find that topics are best looked at as groups of words, and those are independently interesting because they give us a sense of what the document is about. So if a document is associated with some topic with high probability, we're gonna find that the document is going to be really about that thing rather than giving us the sort of ambiguous signal that a token count does. Similarly, we don't really extract semantics when we use token counts. We just have these individual words, and whatever's around the words is unknown, right? But with topic models, we're going to find that the topics do have more definite semantics than the token counts do. And then finally, with text analysis, we're just looking at single words currently, and topic models are going to have support for bigrams, so support for pairs of words that occur in sequence, and using those as single tokens. Okay, so now we're going to get into the kind of the meat of topic modeling. What is it, and how does it work? So first of all, to contrast topic modeling with supervised classifiers, let's talk about decision trees. And we're going to say decision trees are discriminative models, right? And what does that mean? It means, first of all, that they aggressively model the classification boundary. So decision trees aren't concerned with any other aspect of the data. All they want is to know what is the best way to determine the class. That's all you're trying to model with a decision tree. And also, they're going to be parsimonious. So we're not going to consider a feature in a decision tree that we don't absolutely have to model the classification boundary. So this, in practice, leads to models like the one we saw. It looks for those features that, as quickly as possible, will get us to a decision about the class. That's fine. That's a good way to get to a prediction for the class, but it doesn't often tell us too much about the data. In that case, again, all it told us is there were this whole bunch of bits of web content that involve food, and those bits of content are evergreen. And it seems like pretty much everything else is going to be labeled non-evergreen. You know, again, a good way to build a classifier, but maybe not a good way to discover some of the interesting bits that are inherent in your text data. Topic models are sort of the opposite. These are generative models. And what we mean by a generative model is essentially you use a theory of how the data is being generated. So rather than trying to just model a classification boundary, you're trying to come up with a process to parameterize a process that explains everything about the data and how it came to be. And basically the process of fitting that model, the process of parameterizing it, is to use the data you have to tweak the parameters in your theory so that they're likely to have generated the data. Okay, now that all sounds kind of hoity-toity and very, you know, academic and high-minded. Let's look at what this looks like in practice. So basically, we're going to imagine a process. As we said, we're going to imagine a process of generating the data, a theory of how the data is generated. So basically, the first thing we're going to introduce is this idea that we have a machine that can generate a random word with equal probability for each poll. So it might generate the word shoe, asteroid, flashlight, pizza, whatever. It's gonna generate all of those words with equal probability. And then if we pull that lever a whole bunch of times, you'll notice that we can generate any sort of document that way, right? If we pull the lever over and over, we might generate some sort of random set of words: shoe, asteroid, flashlight, pizza, some kind of crazy document. We do it again for a new document, we get kind of another random set of words. But eventually, in the monkeys and typewriters sense of the phrase, we'll get all of the documents in our collection. So eventually, we'll generate that blob of text that we saw before. And we can model any document creation like this, where we just have this machine that randomly spits out words. Now, the question is, how can we tweak that model? How can we parameterize that model so that it's more likely to generate the words that we actually see, or generate the documents that we actually see in our collection? So the intuition here with a topic model is that written documents are usually have some meaning, and usually that meaning has to do with the fact that the words in the document are clustered around a certain idea that we're going to call a topic. And for a random machine, when we say topic, we mean a version of that machine that has a higher probability for certain words. So suppose we have a machine that generates documents that are about travel. We're going to modify those probabilities so that words like travel and airplane have higher probability of being generated, and words like Mars and mantle have lower probability. And so in this way, when we pull that lever, we're more likely to get a document that's about travel. Our documents that are about travel are more likely to be generated by this machine. Similarly, we can have a machine that's about space, and the same thing is true. When we pull that lever, we're more likely to generate our documents about space than we would with our random machine. And so now let's imagine we have K of these topics. We have K of these machines that generate random words. We're going to concatenate all of the text fields in each row of our data set into a single document. And then we're basically going to try to figure out the K machines that are likely to have generated these things. And again, each topic is represented as a distribution over words. So some terms, some words have more likelihood of being generated than others. And our challenge is to take our set of documents that we actually observe and use those to determine what the probabilities in those topics should look like. What kind of machines are most likely to have generated those documents? So again, let's see what this looks like in practice. So we're going to go back here to our StumbleUpon data set. I'm going to do configure topic model just to show off what this looks like. So basically, the topic model is only going to use text fields, so it's only going to use these two text fields. We can select the number of topics and the number of terms we're going to see for each topic in the interface, and then also a term limit, how many terms we're going to keep track of for the model to use. And I'm going to create a topic model right now. Now, remember, this algorithm is trying to make a theory of the data. It's trying to come up with a comprehensive mechanism that is likely to have generated the data. So as such, these generative models are going to take, in general, a bit longer to learn than, say, a decision tree, which is only trying to model the classification boundary. So this StumbleUpon data set has a few thousand instances. It might take 1, 2, 3 minutes to finish. I don't want to sit here for 1, 2, 3 minutes, so I've already trained this model once. And so let's just take a look at what comes out of that process. So here's the StumbleUpon topic model. We have 2 views for you to look at the topic model. The first one is this one, sort of a topic map. And basically, the idea here is that each topic, each machine in your data, is represented as a circle, and the size of the circle corresponds to how much of your document collection that topic explains. How many, essentially, with a lot of simplification, many documents are generated by that topic. So this topic, for example, sports, game, swimsuit, team, Olympics, these are all sorts of things that appear in Sports Illustrated, basically. It's a fairly large circle. And so this is a topic that explains quite a bit of your data relative to the other topics. A lot of people tend to recommend and bookmark things that are related to Sports Illustrated. And so if I want, I can change the name of this topic to Sports Illustrated, which is a US, for those of you in other countries who aren't aware, it's a US publication that focuses on sports. And so now you see the text changes. I've renamed the topic. So I've got a good, I can get a kind of easily get a good sense of what topics are in my data and how they're related. That's the other thing about this view, is that topics that are closer, the circles that are closer to one another represent topics that are kind of semantically related. So let's go down here, for example. Here's a topic with the words cup, baking, butter, minutes. Obviously, this topic is about baking. I've renamed it baking and measurement. And then all the topics nearby, chicken sauce, cooking, add oil, etc., are about cooking. Here's another topic about cooking. In particular, this is looks like it focuses mostly on eggs. And then here's kind of a chocolate, sort of a cookie, candy, brownie topic. And then way down here, you see the elaborate desserts topic with cake, ice cream, cupcakes, cheesecake, etc. So we can get very specific with these topics. It's able to kind of tease out the different things, the different sorts of ingredients that occur in different recipes. Here's cheese potato grilled. This is like the savory topic up here. And then over here, we have kind of a general recipe topic that has all of the more general words you might find in any recipe. Yeah, and so I've labeled several of these. Here's one about technology. Some of these are going to come up later in the demo. That's why I've labeled them. And then you've got less common topics. This one is just about research on the human brain, it looks like. And then you've got kind of vague topics. So these the topics that you'll find in the data that are kind of the most fun are the ones that don't really correspond obviously to a real life category. So I've labeled this one self-help. That is a real life category, but you can see the words in the topic are words that would, unless you saw them in combination, you wouldn't really be able to figure out what documents containing these words were about. So if a document contains the word people, that can be about anything. If a document contains the word time, that can be about anything. But when you see documents that have kind of all of these words together, life, people, change, yourself, help, mind, you start to get the feeling that this is the self-help topic, right? And so I've labeled it as such. The other view we have available to view the topics is the term chart. And here you can see it's basically on the y-axis there you see all of your topics listed, and on the x-axis you can see a little bars of different size that show how much of that show the probability of that topic generating that term. So you can see way down here in the general recipe topic, the word recipe explains most of the topic. Whereas there's other ones like this one. This topic is just about colors. So there's the word color, the word red, green, box, white, blue. A lot of these are about image processing, so it's mentioning the colors here. It's also mentioning various words associated with image processing like box and things like this. This is kind of a topic where all of the words are equally important, and the recipe topic, for example, is dominated by the word recipe. Okay, so that's interesting. We can pass it this pile of text data, just a bunch of blobs of text. In that case, it was web pages essentially, but it could be anything. It could be any series of text blobs. So what might you use this for? The most basic thing is as a preprocessor for other techniques. So if you want to pass the results of that topic model to like clustering or supervised learning, you can do that. It's going to require the ability to assign a topic score for each of those topics to any given instance, which we're going to see in a little bit. But that's one way you can use the topic model. One way is to bootstrap categories for classification. So I was on a project once in a previous job where we had the users scanning big piles of documents. If they had a bunch of paper laying around, they could scan thousands of documents. And one way to figure out how to categorize these documents was just to get a bunch of documents that are very similar together and say, hey, what about this group? Is this something you want to, automatically label in the future? And then they could say, oh yeah, that's all my receipts, or oh yeah, that's all my purchase orders, or no, that group of documents isn't very important, it's just a coincidence. But either way, you can come up with categories with your topic model kind of organically from the data set, and you can decide that whether those classes are important or not to you in the future. Recommendation, it's an obvious way to assess similarity between documents. So if you have resumes that are similar, you can route them to the right HR person, or if you have blogs that are similar, you can recommend them to other blog readers, or so on and so forth. Possibilities for recommendation are kind of endless, and at this point, a lot of them are being exploited even now. And then finally, just for discovery. So a good example of this, I have some friends in the legal world where they use technology like this to figure out what's in a huge document collection. So as part of the legal process, in the US at least, often the prosecution will dump a huge amount of data onto the defense in the name of disclosure. They have to show you everything they have at some point in the legal process. And the challenge for the defense is to kind of look at all these documents and figure out what's relevant and what's not. And this is a way of doing that. You just take all those documents and put them into a technique like this, and oh, here's the topic about financial stuff, and here's the topic about that's just kind of general gossip, and here's the topic about, if you have a whole bunch of emails, you can imagine the things people might email back and forth about. And you get a sense right away of the list of things that's present in that collection, in that heterogeneous text collection. Okay, so as I said before, an important part of the topic model is to be able to predict a topic distribution for instances that weren't in the training data. You always want to be able to use the model to explain stuff about data that you didn't use in training the model. So the idea here is that usually a document, if it's long enough, is going to be a mix of topics. It's not going to be generated by just a single topic. And we're going to represent that as a distribution over topics, so a distribution of topic probabilities. So a good example of that is we have this document, will 2020 be the year that humans embrace space exploration and finally travel to Mars? Obviously, this is about space, right? And so we assign a high probability to the space topic. We say that most of these words were generated by pulling that machine that gives us space words, essentially. But then also, this is about travel, right? We said the word travel. It's about exploration and going somewhere. So some of these words could have been generated by the travel machine. And so we'll assign a lower but still significant probability to the travel topic. So again, when we talk about traveling to Mars, we're mostly talking about space, but also we're talking a bit about travel. And so we can actually do that with our trained topic model. We can go back here and on our one-click menu, we can go to topic distribution. And if you remember, I trained this topic model with 2 text fields. The URL, we're not going to use the URL, so I'm just going to disable it. But keep in mind that no matter how many text fields there are, it's important to realize that all of the text is concatenated to make a single document, as we said at the top. So right now, we don't really differentiate between these 2 fields. So I'm going to type in here, and let's type in some words here. Let's type in change your life. And you can see the self-help topic jumps right to the top. not really a surprise. Change your life is kind of a loaded phrase, and it's definitely related to self-help. But if we add the words with science, now we start to equivocate a little bit about what this document is about. It could be about self-help, that's true, but what else might it be about? It might be about a product you can buy that improves your health, right? I've labeled that topic. And then it could also be about technology, right? This is so. What sort of science changes your life more than new technology? So you can see, again, we're starting to hedge a little bit about what the document is about based on where these words might have come from. And so now let's make it a little clearer. Let's say, did you know that most people are smarter after a good night's sleep? Okay, so now this is clearly about, getting your sleep and trying to improve your life by getting more sleep. And so self-help is still very important, but now this sort of habits and daily routine topic has come to the front. So words like sleep and drink and stress and feel, those things have become very likely for the model, and with good reason, right? If you're talking about improving your life by getting a good night's sleep, habits and daily routine topic starts to be appropriate. And then you'll notice way down here we have some other ones. It still might be healthcare products. I mean, how are you going to get a good night's sleep, right? And maybe they want you to buy something. But also there's this brain research topic that, you're talking about getting more sleep and being smarter. It could be about brain research. And probably there is some research underpinning a result like this. So again, our intuition about what this document might be about so far matches kind of what the topic model is telling us. So let's see if we can make it more apparent that this is about science. So instead of did you know, let's say that studies show that most people are smarter after a good night's sleep. The brain research topic is now looking a lot more likely now that studies are showing something. And then maybe most people aren't just smarter. That seems like kind of a non-science-y way to talk about it. Let's say most people have increased levels of cognitive function. Oh yeah, now we're in science. So now it definitely thinks, after all those kind of science-y sort of buzzwords, cognitive function and whatnot, now it's pretty sure this is about science. More maybe than just self-help or habits in your daily routine. But still, habits in your daily routine and self-help topics are non-trivial probabilities. It's just saying that this document is more kind of science-y with all those science buzzwords in it than your average self-help document. So again, the bars here kind of correspond to intuition. One thing I wanted to point out about this, let's just go back to the beginning. So now all our topics are equal probability. There's no words there. And let's just type in the word cognitive. Of course, brain research jumps to the front, as you'd imagine it would. Why does it do this? You'll notice that in the list of terms here, in the list of most likely terms for brain research, cognitive isn't there. This is because the word cognitive is a fairly low occurrence word, and it's not even after saying, okay, this document is about brain research, it's not a likely word to be generated. It's still fairly academic and niche. But for all the other topics, there's absolutely no reason you'd say cognitive. There's no reason you'd say cognitive if you were talking about your cookie recipe. Or I can invent something crazy, but probably you won't say cognitive if you're talking about your cookie recipe. And so because even if the probability of generating that word is fairly small for the brain research topic, it's nearly zero for all the other topics. And so that being the only word there, we decide that this is probably about brain research. Okay, so the last kind of major piece of topic models is the ability to do that for a whole bunch of instances. So that's nice that I can predict a topic distribution for a single instance. But let's suppose I want to do it for a whole bunch of instances. I have tens or thousands or millions of bits of text that I want to assign a topic distribution to. So we do this for clustering, right? We have unlabeled data, we do a clustering, and then we can do something we call a batch centroid, which is basically process all the data in batch and add a column to the unlabeled data that has the centroid in it. So whatever centroid is most likely for that data point, given your clustering, we append that to the end of the data set. And similarly, we can have the unlabeled data, we can construct a topic model from the text fields, and then we can do something called a batch topic distribution, which is the analogous thing. Basically, we append columns to your data set, each column of which is a probability for that topic, given the document in that row. And so just to take a look quickly at that, it works hopefully more or less exactly as you expected. We'll go back to our topic models. And we can do a batch topic distribution. And we'll just use the existing data set. You can see we have the URL boilerplate and the label, and then also we have all of the different topics. You'll notice that the names that I gave the topics propagate through into the header here, so the baking, measurement, Sports Illustrated, etc., have all propagated through, and I'll construct the topic distribution. So here's what we get out. Let's take a look at the output data set. And then just to kind of drive home the point, you can see we have all of the topic scores. This is the baking measurement score. I didn't label these topics, but here's the Sports Illustrated topic score. So we have a score for each topic that's some decimal number between 0 and 1. For most documents, obviously don't have most topics. Most documents are only about 1 or 2 things, so most of the scores will be close to 0. But let's try to predict. We'll deselect our text features here, and let's try to predict the label from the topics instead of from the actual text. So obviously we want to change our label to the label, the evergreen 1 or 0 label, and we'll create another model. And so here we have the same model. Basically, we're trying to predict evergreen or not, except we're trying to predict it from those topic scores for all of the instances in the data set. So you'll see, as before, the recipe topic or the recipe idea is very important here. So if it has a high score for general recipe, you can see that again we're pretty confident that this is a evergreen bit of web content. And then if we keep following down, if it's also high for baking and measurement, so on and so forth. If we go on this side, we see other scores, but you'll find that a lot of these topics near the top of the tree again are just trying to figure out whether or not it's about food. And then further down the tree, you have some of the other topics. I think I saw technology. Yeah, technology in there for a second. So if we get this far, we're pretty sure that it's an evergreen bit of web content. But suddenly, if it has a very high technology score, it turns out it looks like it's going to be technology about baking or food preparation. That tends to be kind of ephemeral, right? Because the release of a new device that helps you do cooking or baking is only going to be relevant right around the time that device comes out. So that's nice. We can get a bunch of new features for our document. We can kind of embed our documents into a new feature space based on this topic model, and we can do all of the things we're used to doing with our data in a completely new feature space. So we can still do clustering or anomaly detection or supervised learning using those topic scores as features. The very last thing I wanted to touch on here is tips for kind of tailoring these to your data, tips for making your data work a little nicer with these topic models. First of all, you have to set K. This is kind of the same unfortunate thing that you run into with clustering. You have to know a priori how many topics you want to be fit in your data, and the setting of K can dramatically influence the results. So just like in k-means, there's no easy way to say what's the right size for your data. If you have auto auto-determine selected for the topics if you want us to determine it automatically. Then we try to fit as many topics as possible as long as you have kind of enough data to fit those topics. So once you get over several hundred or 1,000 instances, we start trying to fit a lot of topics. And the reason for that is because if you have too many, you're going to partition highly related topics. But if you have too few, you're going to agglomerate topics together, right? And the latter or the former thing, agglomerating topics, tends to be a bit worse. Because when you agglomerate topics, all of the probabilities kind of smear out, right? You end up with a single topic where the frequency of those words just matches the frequency of the words in your data set, which isn't very interesting. Whereas if you have too many, maybe you end up with some redundant topics, some topics that are highly related, like we had all those different cooking topics. But even the differences can be interesting. So I tend to kind of set K as high as possible, as high as my data will allow. And once I've got several thousand documents, you're able to set K, pretty high into the dozens of topics and get some nice results. Tuning the model. So if you're getting topics that you don't like, some things to try or that aren't helpful to you, some things to try. Remove common useless terms. I'm going to talk a little bit about that. I think I have a few more minutes. And then also set the term limit higher and use bigrams. The effect of both of these things is to give the model a bigger vocabulary and a few more kind of low frequency things to work with, which may be important, right? If you have a topic that only occurs in 1 or 0.5% of your data, some of those low frequency terms may give nice hints about what the topic is about and what that document is about. And so just to show that briefly, if we go back to our topic model, we see that there's several topics in here that are kind of dominated by these words that don't mean anything. So for example, the token www, which is part of the web address, appears in this topic very highly. You can see it's like the 6th or 7th thing, the 7th thing down on this topic. Let's see, there's another topic where it also appears. Yeah, it's the 2nd thing in this topic. So these topics are just kind of dominated by the token www. It happens all the time, so the topic model thinks it's important, right? It's gonna, if the word is in your data and it's happening a lot, the topic model is going to try to explain that because it's trying to explain all of your data. And it turns out that www thing happening all the time is a big part of your data. But maybe it's not important to you. Probably in this case, it's not important to you. So excluding that term, because it happens all the time, because it composes so much of your data, excluding that term can really open up the space for the model, give it more effort to expend elsewhere, modeling terms that occur less often and are more meaningful. So if I go back to my StumbleUpon dataset here, and I configure the topic model. Here, as I said before, you can set the number of topics, set the term limit, which is the number of terms that you're keeping track of. So if you want those lower frequency terms, you can increase this. And then finally, over here, we have the ability to include bigrams or stop words. If some of those stop words, a and the, if you find those important, and also bigrams, so pairs of words that occur together, like United States or Supreme Court, you can include those as single terms. And then, as I was saying a moment ago, we can exclude terms here too. So if we wanted to exclude www or com, which happens a lot in that data set, HTML, things like that, tokens that happen a lot in the data set but don't mean anything. Often if you model with those things excluded, you can get a very different model because, again, so much of your data set is composed of those tokens that are too frequent and also not very meaningful in the context of the document. So thank you very much. That's all I have for right now. Remember, you can reach us on Twitter or at our mail account, and you can see the documentation for this release at the address on the slide.